Hello. Okay, so now before we get started with this next session, or excuse me, section or subsection, what I want to say is up until this point we've talked about these isomorphisms, these relationships, these mappings, these as far as being like this, the same as, right? And we keep using this term that we're saying that these two vector spaces, or these mappings between these two vector spaces are the same, right? Or we use this quote unquote the same as. Well, in this section we're gonna make that more precise because we're gonna talk about two different vector spaces as being the same by showing that there's actually an equivalence relation between the two. So it's almost equal. So we're taking two unequal spaces, right? And we're saying they're almost equal. In other words, we're going to say, hey, there is a correspondence between these, and what we're going to show is that it's an equivalence relation, and that's what we're going to start with. And so we're going to start by introducing a lemma, and this is going to be lemma 1, and showing that there is a correspondence. Not only we're going to talk about inverse, there's an inverse function, inverse mapping, and that there's a correspondence as well with that. So let's start by introducing the first lemma, which is lemma 1, and it says the inverse of an isomorphism is also an isomorphism. Okay, so we talked about isomorphisms, right? This is where we talked, introduced the idea of an isomorphism. We said, hey, we're going to use this quote unquote same as or same. So we're going to start with this idea, and lemma 1 says, hey, the inverse is also an isomorphism. So we're going to prove that, and so we're going to start with this part of the proof, and then I'll continue on and we'll finish it up. But the proof says, suppose we have this vector space V is isomorphic to W. In other words, we have this function from V to W, okay? That's isomorphic. So there's an isomorphism there. It says an isomorphism is a correspondence between the sets. So F has an inverse function, right? So there's a correspondence, which means onto, one-to-one and onto, right? So there's going to be an inverse function from W to V that is also a correspondence. So what we're going to show is that because F preserves linear combinations because it's isomorphism, so also the inverse function F inverse is also. Okay? So we're going to show that this also preserves linear combinations. So in order to do that, let me get I sometimes drop E's. So suppose that we have these two vectors in W, and because it is an isomorphism, S is onto, and there are a vector V1 and V2 in V such that vector W1 is equal to the function F of V1, and W2, the vector VW2 is equal to F of V2. Okay, and so what does that give us? I'll show you. So if that's true, okay, so again, F preserves linear combinations, right? Inverse function also has a correspondence. Okay, so we're going to use that information to show that the inverse function also preserves linear combinations. Okay, so let's start with that. Okay, so we're going to start with this. So again, pause the video, take notes. Okay, so here's what we have. Okay, we take our linear combination. Okay, F inverse of C1 W1 plus C2 W2. Okay? And so now what we're going to do is we're going to show a string of equal signs, right? Showing that we can get back to a linear combination using the inverse function. Okay? So the first thing we're going to do is we're going to show, okay, well, W1 and W2, we know that's going to be the same as with the function. So we're going to have if inverse, of what? We're going to have C1 f of V1 plus C2, f of V2, right? Parenthesis. Okay, but now we know that f preserves linear combinations, so let's do that. Let's use that. So we're going to now bring in the combination. So this is now going to be f of C1 V1 plus C2 V2. And again, that's just from the fact that it preserves linear combinations, right? That's given to us. And now notice that obviously an inverse of a function, right? So these are going to cancel each other. So now we're just going to get the argument out. So it's just going to be C1 V1 plus C2 V2, right? And now here's where we're going to include the inverse function, right? And this is where we know that that the inverse function exists. So now what we're going to do is we're going to say, okay, we're going to substitute V1 and V2. Okay, how are we going to do that? Well, we know this, right? So C1, and now we're going to do F inverse of W1, right? We're just using what we were supposing, plus, let's write it over here, C2 F inverse of W2. Okay, so far so good, right? And now, since F inverse of W1 equals V1, right? Since F, inverse of W1 equals V1, right? Oh, and F inverse of W2 equals V2. Now we can substitute that in. Right? So we can substitute this in here because we know this. This is what we're given. Okay, so far so good, right? So we started with this, and now we went here, because all we did was substitute in for our functions, and then that now, because F preserves linear combinations, we can go to here, and then of course the inverse and its function cancel each other out, right? And we get the argument out. And now, since we know this in this, we can now substitute in and get that. Okay. And then, with that, we're going to use the previous lemma's second statement, and the map preserves structure. Okay, so again, by the previous lemma, right? So this would be the second statement. I think it was lemma 1, if I in the last subsection. By previous lemma's second statement, structure structure is preserved. And we're done. Have a great day.